Hello everyone, welcome to this video. In today's video I will show you a case where a fish trawl hits a subsea pipeline. I'll show you step by step how to do it in ABAQUS. These are the couple of scenarios. So for example, if this is your fish trawl here, as you can see, and this is a simple pipeline. Pipeline will be modeled as a shell. Fish trawl is, in this case, is cubic, but you can use whatever shape you will have. And this gray area is the soil part, which in this case we are modeling it as rigid, but if you know the friction coefficient, cohesive properties, angles, etc., you can use those as well. So you can see in the first step is the gravity step, and in this case, since this fish trawl is really small, and it really drags the pipeline and gets stuck or snagged in the pipeline, and it causes a lot of deformation. Second case, I change the size of the or geometry of the fish trawl, and now you can see with a very high speed when it strikes, so it has some rebound effect and it goes on the top and then it comes down again and then goes with the fish with the ship or board, whichever is really pulling it in that direction. So last one I run with a slow speed, and in this case if you see again the gravity step, and then it goes like this slowly over the top of this and creates a lot of stresses in this area. So speed wise, if you see this speed and this speed for the same geometry, higher speeds are causing a lot of higher stresses as compared to slow speeds. So this is what you're going to learn. So if you are still interested, then keep watching this video and learn step by step how to do such simulations. So see you on the other side. Okay, let's start with the pipeline model first. So I will make a pipeline with a diameter of 0.5 meters and the wall thickness of around 30 millimeters, while I will use the length of the pipeline to be 10 meters. So you go to the part 3D part. I'm going to model it with the shell. If there's a requirement for you to go with the solid model or solid elements, and you can use this solid option. I am modeling it with shell to save my time, and then I will do extrusion. So what I'm going to do now, I'm going to create a circle with a diameter of 0.5 meters. So if everything is in millimeters, so 0.5 meters will be 500 millimeters. So that's what I'm going to do now. So I will give 500, 0 as the dimension for this thing. And wall thickness we can assign when the shell properties. If you are making the solid one, then you can create another circle here, and that should be defined based on the diameter will depend on the wall thickness, which is in this case 30 millimeters. So now I have done this. I will just press done, and then I will extrude it for a distance of 10 meters, which in millimeters will be 10,000 millimeters. And this is the pipe. This is how the pipe looks like. Again, the length of the pipe you can decide how long it has to be. We are just looking at the very local impact of a fish trawl with the pipe. So, and we are interested in the local deformation, so we are going with that. If you want to look at the global one, or if you see some effect coming towards the boundary because of that impact of fish trawl or dragging of fish trawl, then you can basically make the pipe longer. So now what I'm going to do, I'm going to assign the properties first. So we will do it one by one for each part. So I will define the density, and again everything is in millimeters, so I will use the density of the steel to be 7 in tons per millimeter cube, so it will be 7.85 exponent minus 9. If you convert the kilogram per meter cube, which is 7850 kilograms per meter cube for steel. And then I will define the elastic properties. So again, the elastic properties should be, Young's modulus should be in Newton per millimeter squared. So that should be 210 and then 6 zeros. 6. And Poisson's ratio, I'm using it to be 0.3. For the plastic part, I'm going to use bilinear hardening, and you can define it in terms of, you can define it with basically yield strength at the yielding, that's 350, which is at a plastic strain of 0, and then you can define another value of yield strength and that should be, let's say, 400, and that is at the distance of 0.5 string. So again, you can find your actual properties of the material, and you can use the table, or you can use any constitutive model. I have many videos on all these different models, so you can select what you really want to do. Normally DNB or other cores, they go with the bilinear behavior, so initially linear elastic, and then plasticity is also bilinear, which I have done in this case here. So once I have done that, I will create a shell section with the homogeneous properties, and here I will give the value of the wall thickness of the shell, which is this one. The rest is the same material is material 1, which is the steel properties, and then I will assign it to this component here, and the color will change to green. So this pipeline is now ready for everything, and I will now go towards the second component, which is basically the soil, which is the base of this model. So I will again go back to the part, create. Again, you can model the soil as a rectangular shell, a rigid body, and also a deformable body, depending on what is required. In the present case, I'm gonna go with that I would say analytical rigid, right, an extruded shell, and I would go with, let's say, a line, and since the pipeline diameter is 500 millimeters, so I can make it minus let's say 300 on comma 0, from minus 300 comma 0 to 300 comma 0. So it will be like this, and then when I say done, and then I can expand it to 10 meters or even more. Like 10 meters should be fine in this case. So that's what I'm gonna do here, just 10,000, and that will give me this. Now if I put the pipeline here along this length in the assembly module, then we don't have any space for that fish trawl to drag. So I think it's better to increase the width of this thing to much higher value. So I'm gonna go back, and I'm gonna change the sketch here, and I will change these dimensions. So I will go, I can change the dimension, or I can increase the length. So maybe I will just go with some arbitrary values. Oops, let me just move it on this side so it's easier. So maybe this, and then I will do the same, and I will go the same way on the other side. I think it was 1205 or something. So I will go 1205 comma 0, and then if I now press close and done, and then I have to regenerate everything. So I will click, right click, and regenerate. So now I have enough space in the lateral direction, so I can drag the anchor. Okay, this is a rigid part, so we don't need to assign the properties, but we might have to assign firstly the reference point. So I will go back to the part, and I will create a reference point. I can use any place, for example this one is a reference point, and then in the property module we might have to assign the inertia, because there has to be a mass, because we will be doing explicit dynamic analysis, so we need to define the inertia properties for this. So I'm going to go with the point mass inertia. I will select the point to assign the mass and inertia, which is this reference point, and again you can give a value of mass of this thing depending on the density, and you know the volume. I'm just using some arbitrary value for now, 1000, and the diagonal values are 1 in the case of rotary inertia. It's gonna be fixed, so it's not gonna matter much, but we need to have it for the case of analysis. If you're using a deformable elastic body, then you don't need to assign this. Rather, you can define the density, Young's modulus, and Poisson's ratio, as I did it for the pipeline case. Now we go and model the third part, which is the fish trawl. Again, fish trawls have very different and complex shapes. So what I'm gonna do is I'm gonna create a simple I can go with a 3D block or 3D sphere as well. You can consider whatever it is. So I will call it fish trawl, and I will call it deformable 3D. Again, you can make it solid or you can make it cube or make it shell as well, depending on what the shape or geometry. I'm going to go with a solid shell. And now the dimensions of the cube, let's say I'm going to go with 500 by 500. So I'll start from 0, 0 and then 500 comma 500. And now if I press done, I need to give a depth, which again is 500 in this case. So this is kind of an idealized shape of a fish trawl. We can again make it elastic or rigid in this case, and to save time, computational time, if it's rigid, if it's elastic, then you go to the properties, define the material properties, create a section, and then assign it to this, as I did it for the case of pipe. If it is rigid, then you can go with that as well. So let me go with the elastic properties. Let me make it an elastic one rather than the rigid too, although it's going to take a long time. So I'm going to use the same properties as steel as elastic moduli, but and density also, but I'm not defining any plastic properties, so it will be always be elastic. We can make it rigid later as well to speed it up, but for the now I will do that. And again, solid homogeneous material 2, and then we assign it to this, which is section 2 material 2, and done. So now we have defined 3 components and we have defined 3 properties. Now I will assemble them together. So I will bring all these 3 components here, so they look something like this. So we need to first arrange them. I think the block, we need still a bigger floor or soil, because if I bring the block here somewhere and then I move it like a fish trawl too, so that it impacts with the pipe and drags along, then we need a much wider soil surface. So I'm going to go back again to my soil and I will increase the length further. So now what I'm going to do, let's say minus 5000 comma 0, and similarly I would do the same 5000 comma 0. Now I will check again how does it look. Regenerate, go back to the assembly, and now I think I have enough space there. Okay, so I would now start moving the stuff and arranging the stuff. So first thing I would do, I will move the fish trawl, and let's say from here to here. So I will move this edge and I will align it with this edge here. Okay, so fish trawl will move in this direction with some velocity depending on the ship or boat speed, etc. And now I'm going to move the pipe and I will try to align this pipe. It's going to be tricky. Okay, so I will rotate to make it a better view, and I will bring first this, bring this point to the middle, which is somewhere here, I hope. Okay, and now as you see, if you rotate it, you still are on the halfway of the pipe, so your pipe is half buried. You can start with that if you have elastic soil, you have a good soil data, but in this case I'm going with simple analysis. So now I need to move it up. So what I'm going to do is I'm going to further then, and I'm going to further move it in the vertical y direction. So I will start from here, right, and then I will move it in y direction to a distance of 501 meters. Oops. So again I will try again, sorry. So start from this point, no, start from origin, which is somewhere here, and then I will move everything to a distance of 500 because it's a relative motion to the origin, sorry. So it should be 0, 0, 0, and then 0, 500. This is how it looks like. So now if you look closely, your pipe is slightly above the thing while this is touching the floor. Okay, your reference point for the floor or soil is this one. Okay, so this is how your model actually looks like now. And now we go to the step. So first thing we're gonna do is we're gonna create a gravity step, right? So we go to dynamic analysis, everything is on, 1 second, and I keep everything default for the now, and then finally I will do a second step where I will drag the anchor. Okay, everything again is default. If it's too slow, you can use mass scaling as well to speed up your analysis. Again, I have a lot of videos on mass scaling and other regularizations. So now we have done the steps. We go to the next stage where we have to define the interactions, and I think the best way is general contact because everything is 3D. And since part 2, which is this part, is analytical, so we need to define the surfaces. Okay, and so we need to define the contact interaction properties. So again, if there are different interactions, so for example fish trawl friction with this thing is different, and similarly friction between this and this is different, then you need to define multiple contact properties. So in this case I'm using a tangential behavior to be frictionless and normal behavior to hard contact. But again, if you have, for example, given the seabed pipeline interaction coefficients are given, let's say you can use 0.5 or something, and similarly for fish trawl and pipeline and fish trawl and soil interaction, you can use a value between 0.3 and 0.6, which is conventionally used depending on the material, surface roughness and soil type. So this is how you can actually define the whole thing. And now what I'm gonna do, I'll select the interaction property here. In my case, I'm making everything frictionless to keep my life simple. Okay, so this is done. The only thing we are now left is we need to define the surfaces, right? So which surface will we will be using? So create surface 1, select this rigid part, and obviously the brown surface we have to use for the interaction. So that surface will be taken into account. Similarly, I think that should work, but we will see. Now we go to the load, which is more careful part. So first thing, very easy, I'll go and fix the seabed, right? So seabed is at the reaction point here, and I will fix all the degrees of freedom of the seabed, so it's rigid and it cannot move for now. Now I will fix both the ends of the pipe. Okay, so I will again use the same constraints, and I will constrain this and this end of the pipe. If you keep your shift pressed, then you can select both edges, and then I will say u1, u2 and u3 all are 0 here in these both the ends. Again, if your pipeline is not end supported, you can use some multi-point constraints as well, or you can use simply supported boundary conditions as well. So now this is fine, and the next thing is move this with a certain velocity. Okay, so I will go here, select velocity, and then I will give a velocity. If it is pulled from this side, you can specify velocity on this side. If it is pulled from this side, then again you can specify, and the velocity should be in x direction. And I'm giving the velocity to be, I'm not sure what is the velocity of these fish trawls are, so I will again have to search for that. Let me see if I can find somewhere. 1 meter per second. So let me give a velocity of 1000 millimeter per second, right? Which may be okay, which may not be okay. I'm not sure. We will see. So it's in the wrong direction, so I will go back and modify and change the sign to minus, because it has to go in the negative y direction as this. Now the distance is too high, if you remember. So the velocity is 1000, and if I measure the distance between the two, so let's say from this point until this point in x direction, so the x component is 500, right? Okay, so that's no, this is y component, sorry, this is 3700, right, in y direction. So it's going to take a pretty long time to simulate, because we need to run it for 5 or 6 seconds. So what I can do, I can move it closer, so that's somewhere here, because whatever is happening here might not be interesting for you in many cases. So that's what I'm gonna do now. I will go back to assembly and maybe move it at a distance from this in minus y direction to, let's say, minus x direction to be minus 2000. So it's much closer. We can further modify it to get 2500 or 3000 maybe. That's too close. Okay, so let's go with 3000, although it's going to increase my computational time, but that's okay. I can live with that for now. Now I have to go and loads, and these are all for step 2. For step 1, what we have to do, we have to define the, so I will move this one left, because this is this thing, and this one, which is fixing the pipe, also to the left, and this one stays the same because this is the second step. In the first step, we also need to define the gravity, right? So let me see. So you go to the loads and you define the gravity, and here you have to define the component of gravity. So in this case, minus y direction should be minus 9180, which is the acceleration due to gravity. You have to specify here. Okay, so if we should show somewhere with an arrow, I can't see it, but should be. So now if you look at the loads, this is in second, so you need to move it to the first one. Okay, and this is how it looks like now. So you see the gravity is pointing downwards. This thing is still, you see, out of the surface, so I might move it slightly up, like the way I've done for the pipe, so that when the gravity activates, it slowly goes down like a drop off of the object. So you can do a drop simulation as well in the gravity step, if you know it's dropping and then coming this way. So again, depending on your scenario, what you want to do. So I will go back to this. I will move this from this in y direction. I will move it to a distance of let's say 1 millimeter, and let me see if I can still see something. Okay, no, I still see something there, so I will move it further. Go, and then 0, 0 in the absolute coordinate system. I'm going to move it in y direction again, and that should be, let's say, 50 millimeters. So I think now you should not see anything at the bottom, and it is slightly up, as you can see here. There is some clearance between the two and also in the pipeline. So now I think most of the stuff looks okay. Interaction wise, we have defined the contact properties. Remember, if you have different soil and fish trawl, and also fish trawl pipeline and soil, and also pipeline and fish trawl friction coefficients, then you have to go and define these contact properties separately, and then you have to define these interactions separately. Okay, I move it to the left as well. So now loads are defined, in my opinion, all correct. So I will go to the mesh, and I will individually mesh each component. This one cannot be meshed, that's why you see it in this color. So I will go with this. I will choose this mesh size. I just want to show you how it works. So this is like a pipe shell model, and for the fish trawl, again I will go with this. Okay, and this is still pretty fine. So what I'm gonna do, I'm gonna make it 25. No, not 25, but 100. See how many are there. Delete mesh. Apply OK, and then mesh again. So for this analysis, we are not looking at the accuracy. It looks something like this. Now is the time to test. Everything is working fine. So I'll create a job. Okay, so I'll call it this job here. I will go with always with double and full precision and full nodal output precision to be full. If there are any number which are very small or big, it works fine. Okay, and now I will try to run the simulation. So if everything is defined correctly, it should go to the process the input file processor, and then it will go to the main analysis. So now you can see it is going for that. There are no errors yet. There are some warnings about output and boundary condition, but they are usual warnings. And these quantities which are being asked by default by ABAQUS are not available for certain element types like rigid ones or non-rigid ones. So it is running, and once it finishes, then I will get back to you with the results and see if we need to modify something or not. One thing which I have missed here, because we still haven't computed the distance. We have given a speed of so it's running fine, but I need to ensure everything is fine. So the speed we have specified here is 1000, and the distance I think now is from here to here is 700. So in 1 second it will travel up to 700 and it will hit the pipe, and then if we keep on running it, it will take longer. So we need to go and change the step time here from 1 second to maybe 3 seconds or something, so that it can go through at least 2.1 meters, which is on the other side. Okay, so this is the only thing you have to change to make it run for a longer distance. Okay, so if you monitor now, you see it's going fine. It's going to take some time. What I'm going to do, I'm going to kill for now. Okay, and since I have changed the step time now, so I will resubmit everything again, and I will show you the results when they are ready. So see you on the other side in a few minutes. So as you can see, the results are finished. I have changed the geometry slightly for this. So what I did was I went to the part module and I increased the height of this fish trawl in this case, and this is run with that. So if I press the contour plots, then you can see it looks something like this. So remember, the first step was the gravity step. So in this step, both of this pipeline and the fish trawl falls down and comes in contact with the soil and comes into in static equilibrium, and that's until 1. And now the fish trawl will start to move with a speed of 100 millimeters per second, and as you see, it moves like this. Again, I have applied the velocities here. Depending on the actual case, you can create a reference point here, constrain the relevant surfaces where this thing is tied, and then you can pull all this reference point as well, or you can apply components of velocities in different direction to get a resultant velocity in a specific direction. So in any case, this is how it has an impact, and it passes over the pipeline, it falls down in this case, and then it slides over the pipeline and goes forward like that. So this is how the simulation is run, and I've already shown you at the start the videos as well. So I hope you like the video. If you have any questions, then please comment below. If you want me to create some more interesting videos, then please do like and subscribe to channel. If you don't like the videos, then definitely these will go, all the efforts will go in vain, and I will end up with no more videos coming in. So thank you very much for your time, and have a nice day.